Welcome back, everyone. On behalf of Forge College, I'm absolutely thrilled to have you here for today's explainer. Think of this session as our master blueprint. It's basically a true engineering schematic for understanding how Ethereum accounts actually live and breathe on the network. Since we're working our way through Ethereum fundamentals, specifically looking at Ethereum accounts and models, and digging into account interactions and the account lifecycle, we're going to map out the entire life of an account. We'll follow it from the exact moment it's created to how it mutates state, all the way down to its potential termination.
Now, I know we just wrapped up our last lesson on development lifecycle practices using the Solana CLI. So let's all just take a collective breath, all right? We gotta switch gears. Goodbye, Solana CLI, and hello, Ethereum blueprints. Honestly, don't even worry about the context switch. We've drawn up a really crisp, highly technical, yet incredibly straightforward schematic to guide us through these fundamentals.
Okay, let's dive into this. Here's our table of contents for Tuning's engineering schematic. First, the post office metaphor. Second, account lifecycle stages. Third, the transaction workflow. And finally, key takeaways.
Kicking things off with Section 1, the post office metaphor. This is our conceptual foundation. So, I want you to think of an Ethereum account as a highly secure post office box. Just picture this box existing inside a massive, sprawling city of ledgers. It's actually a lot like a real mailbox. It gets created when the owner registers it, it just sits there, and eventually, well, it receives mail. In our case, that mail comes in the form of transactions or smart contract calls. And when that mail is processed, the contents of the mailbox get updated right there in a central registry. This actually illustrates a distinction that you absolutely must master. We really have to separate what the account stores from what the network actually does. Think of the mailbox contents as the account state object itself. So its balance, its sequential nonce, its code if it's a smart contract, and its storage. But then, entirely separate from that, we have the network actions. The network is the post office infrastructure itself. It's receiving the mail, sorting it by verifying and ordering the transactions, processing those state transitions inside the Ethereum virtual machine, and then finally recording the whole shebang into the official canonical registry. You know, the state trie. Let's move to Section 2 and see how this builds. Account lifecycle stages, tracking the actual account journey. There are basically 6 lifecycle stages of an account from construction to demolition. We start with creation, move into an idle or existing state, enter into an interaction during a transaction, lock in state persistence, trigger a nonce update, and potentially end with termination. Understanding these 6 exact steps is absolutely your key to avoiding some really unexpected behaviors when, say, multiple transactions hit the exact same account all at once. So let's walk through this linear flow. It begins with creation. Now, this can be implicit, like when funds are simply sent to a completely unused address, or it can be explicit, like when you deploy a smart contract with initialization code. After that, it just sits in the idle state, waiting quietly in the state trie. Then, when you send a transaction, boom, we hit interaction. The EVM executes code, which might change balances or storage, but keep in mind, those changes aren't permanent until stage 4, persistence. That's where the state trie root is updated in an actual block. Then, and this is crucial, in stage 5, the sender's nonce updates. Finally, stage 6 is termination, where a contract might use the self-destruct opcode to completely clear its code and storage.
Now, let me ask you a question that pretty much every Web3 developer has asked themselves at 2 a.m. Why do transactions suddenly get stuck or fail? You've built your interaction, you hit send, and literally nothing happens. It just hangs there in the void. So frustrating, right?
Well, the answer almost always comes down to the 5th stage of our life cycle, the nonce. I actually like to humorously explain the nonce as that little sequential paper ticket you pull at a super crowded deli counter. The network consensus strictly enforces that for any given sender, only the transaction with the next exact sequential nonce can be included. So if you're holding ticket number 5 and you try to hand the butcher ticket number 7, yeah, you're going to be ignored. You absolutely cannot skip numbers, and you definitely cannot replay a ticket number you've already used. It's a strict system deliberately designed to prevent out-of-order or duplicate processing. Which brings us to Section 3, the transaction workflow. Let's look at the step-by-step flow. Now, what's really interesting about tracking a single piece of mail through its life cycle is watching how observability shifts at each exact point. We basically jump from constructing the transaction to throwing it into the mempool, then execution in the EVM, finalization in a block, and finally, observability by the outside world.
Let's inspect what's actually happening to the account at each one of these steps.
Starting with step 1, you construct and sign your transaction. You're setting your planned nonce, your gas limits, your data, and your signature binds that whole package to your account's key pair. But remember our mailbox metaphor? Right now, all you've done is seal the envelope and put it in your local outbox. There are absolutely zero canonical changes to the official Ethereum registry at this point.
Next, your mail actually hits the network, and we see a massive contrast between the mempool and execution. The mempool is basically chaotic, tentative sorting. Miners and validators are judging transactions based on gas incentives, and your transactions might literally be racing against each other. But once a miner actually picks your transaction, we move into execution. The EVM processes the state, debiting balances, changing storage, but here is the vital secret. Those intermediate state changes are visible only locally within that specific execution context. The rest of the network cannot rely on these changes quite yet.
Let me walk you through this technical specification, because this tells you exactly who can see what at each specific stage of the workflow. During construction, only the sender sees the planned nonce. In the mempool, there's no persistent change. It's just miners observing pending mail. During execution, balances and storage change, sure, but only the execution context, and nested calls within that same transaction actually observe it. It isn't until finalization that all the full nodes finally observe the updated nonce and balance. And if a contract happens to hit termination, well then all readers see the storage completely clear.
And that leads us perfectly into steps 4 and 5. Finalization and observability. Once a block is finalized, the mail is officially recorded in the state tree. The account's new balance and that freshly incremented deli ticket nonce are now officially visible to all peers. Any RPC queries from off-chain indexing services will now return those newly committed values. The race is over, and the sequence is completely locked in.
So, the crucial point is summarized in Section 4, Key Takeaways. Let's review the fundamental rules.
Okay, here are your 3 core takeaways from today's blueprint. Number 1 is atomicity. Transactions either perfectly apply their state changes to the block or they fully revert. There is absolutely no partial commit on Ethereum. It's all or nothing. Number 2 is nonce sequencing. You must manage your ticket numbers strictly to avoid stuck or conflicting submissions from the same account. And number 3, visibility boundaries. Never expect another caller to see an intermediate storage write before a transaction actually finalizes. Visibility relies entirely on block finalization.
I actually want to read you this quote directly from our lesson text because cementing this post office mental model is really your ultimate sanity check for avoiding bugs. Quote, "The account stores contents, transactions are mail, and the network sorts and commits mail to the registry." Whenever you're trying to reason about some complex interaction, just ask yourself, who has the ticket number right now? When is the mail being sorted? And has the registry actually recorded the change yet?
Which leaves us with a final, somewhat provocative thought to ponder. If a contract undergoes the termination stage and self-destructs, clearing its current storage and code, but it leaves historical traces visible in the blockchain's permanent history forever, is the mailbox ever truly gone? It's a fascinating philosophical and technical reality of working with immutable ledgers. I highly encourage you to chew on that. And when you're ready to dive deeper into transaction lifecycle stages or honestly any other Web3 topics, please visit us at forge.college. This has been a Forge College Explainer. Thank you so much for hanging out with me today, and I will see you in the next one.